All right, so for section 4.2, section 4.2 deals with minimal spanning trees, specifically creating minimal spanning trees. So in terms of what we're going to be looking at, the first thing is looking at the definition of our minimal spanning tree. Notice right here, we've dealt with spanning trees. We've actually talked about minimal spanning trees before, but this is some spanning trees, so it's a tree. You don't have any circuits. You don't have any cycles. You don't have any of that in there. It's just pick any two vertices, and there's exactly one path between those any two vertices that you choose. Now, spanning tree means it is a subgraph of some given graph G. Spanning means you used all of the vertices in a graph G, just to remind ourselves. And this is the additional part for the minimal spanning tree is where if you add up all the weights attached to all the edges in your spanning tree, or cost, or whatever lengths, whatever they're actually called in this network, when you add up all of those numbers associated with your edges, that number is as small as possible. Please note when you find a minimal spanning tree, there's not necessarily one exact answer. There is often, well, it depends on the network, but there's often more than one possible minimal spanning tree for your network. Now, the different algorithms that we're going to have, and we're going to have 2.5. The half refers to Dijkstra's algorithm that we talked about last time. Behind the scenes, Dijkstra's algorithm does in fact give you a minimal spanning tree, okay? But we're going to have 2 algorithms today, and these 2 algorithms will give you back a minimal spanning tree, but they're different in terms of how they build that spanning tree. So what that means is you can actually get 2 different spanning trees when you're going through these 2 different algorithms for today. And the spanning trees can be different from the algorithm that you get from Dijkstra's algorithm as well. Now, full disclosure, I was actually totally fixating on finding you guys an example that was relatively small that yielded 2 different spanning trees with the 2 different algorithms. And I'm not going to lie, with a relatively simple tree example, all of the simple tree examples that I was pulling, and it could have also been that it was 1 a.m. in the morning that this issue happened, and I was finding that for both of these 2 algorithms, you actually were getting the same spanning tree. That does happen depending on the simplicity of your graph and how the edges and the weights are connected to each other, okay? So be aware, that's okay, but it's also okay if you get 2 different minimal spanning trees. Now, let us look at the 2 algorithms. Both of these 2 algorithms are actually greedy algorithms. In terms of Kruskal's algorithm, named after a guy, the second one, which is going to be Prim's algorithm, named after another guy. So here's what you start off with. You start off with some graph, a network, so you have to have weights associated with all of your edges. If you don't have weights associated to your edges, you can actually by default put a weight of 1 on each of your edge or a weight of 0 on each of your edge. People do different things, but notice if the weights on all of your edges are exactly the same, a minimal spanning tree is going to be the same as a spanning tree, because if you have n vertices, so let me actually write this down. The selection isn't selecting. Just a second, my cursor's off. There we go. Here, if you have some tree, well, I guess it didn't work take. So if the number of vertices is n, and you build a tree for a tree, you always have 1 fewer number of edges. So notice if all of the edges have the exact same weight, it doesn't matter what spanning tree you grab, the weight's going to be the same. It's going to be n minus 1 times whatever the weight was, okay? So this minimal spanning tree situation really is only something that is applicable if you actually have different weights on your edges. And it could be just that one edge has a different weight from everybody else. If it's smaller, use it in your spanning tree. If it's not smaller, if it's bigger, don't use it in your spanning tree unless you're forced to, type thing. All right, so you're given some graph, it's a network, it's not currently a tree, because if it is a tree, you do nothing, you're done already. Okay? And our goal is to find the spanning tree with the smallest weight possible, or whatever. Remember, weight's a generic term. if these things deal with capacity or deal with cost or deal with length, it's the smallest. Fill in the appropriate word that you're using to describe the number associated with your edge. Okay. First thing that you do in Kruskal's algorithm is you look across the entire graph G and you add an edge to your tree that has the smallest weight and doesn't complete any circuits with the edges that are already in the tree. So notice the initialization step, and let me actually add in here a step 0. Pick the edge with the smallest weight first. And when we talk about weight, remember that's this function. Your author calls it KE. Lots of places call it WE as well. And you keep adding the edges. Okay, so we'll have an example that deals with this. Note, if at any stage you have a tie, so maybe you have 2 edges that you could add into the tree with the exact same weight, well, you get to pick which one you add in first or second. You actually add in all of them if possible, but if any one of them completes some circuit that's already in your graph, in other words, makes your tree that you're trying to build not a tree, don't include that edge. And notice sometimes you'll have choices. So there's not a unique answer with this algorithm. Okay? And then you'll repeat this step right here until you get a grand total of n-1 edges. One of the ways that I think about it is once you have an edge that is incident to all of your vertices is another way to think about that if you don't actually want to count the number of edges. Okay? Now, thing to note about this one here, actually, in terms of this, do I need to worry about? Oh, we already said that. So if a tie for the shortest or the smallest weight, it doesn't matter. Choose whichever. The only caveat is it can't complete a circuit. So as long as it doesn't complete a circuit in the edges that are currently in your tree. Wow, that U was terrible. All right, so let us look at an example, because this is easiest to see by way of an example. And I went ahead and prepped up this example for us, directions, standard directions, which just say, hey, find a minimal spanning tree of your graph. In terms of directions that you would see in the future, you'd see directions that either tell you which algorithm to use or it expects you to pick the appropriate algorithm, okay? So in this case, we're actually going to use Kruskal's algorithm. So let me go ahead and tag what we're going to use. So first thing Kruskal's algorithm says to do is we're going to find the shortest path, or the shortest edge, or typically here you're dealing with weight, the edge with the smallest weight. Anybody guess which edge we could start looking at in terms of edges with the smallest weight? Or perhaps I should rephrase, what is the smallest weight in this graph on our edges? You got it. With multiple answers coming in. Yes. So smallest weight among all of these edges totally is 1, and they occur in several places. So I'm going to highlight the edges that we're going to throw into the graph, and then I'll go ahead and write down. Actually, maybe I'll just color code them because I'm lazy today. Okay. So we've got an edge here, AB. We've got an edge here, JK. We've got an edge here, DK. Anybody spot any other length 1 edges? Or did we get them all? Yeah, I don't see any extra ones either. All right. Now, once you've added in all of your weight 1 edges, the next one up you do is you then look at all of your weight 2 edges. Okay? So if we look through this graph, do we have any edges that have weight 2? Hopefully the answer is yes. Actually, I'm spotting one right now, so the answer is yes. So we're going to add in all of the weight 2 edges that we possibly can. So I'm just going to scan through this systematically. Top row up here, there's nothing, but when we get to the vertical top row, we do actually have a weight 2 from A to E. If we look down here on this sort of horizontal second row, we've got FG, we've got GH. If we look at, whoa, that is the problem with having a scroll touchscreen on my mouse. It accidentally gets touched all the time. Then the next, this sort of middle vertical edges, it looks like we've got a 2 where right here from F to J. The accidental wobble denotation there. Then on this horizontal one, we have I to J. We then have K to L. Horizontal edges here at the bottom, we have L to P. And on the very last row, that's sort of, I think I said horizontal, those are vertical. Horizontal edges on the very bottom, we have MN. Do a quick double check, see if I missed any weight 2 edges. And while you guys are checking to see if I missed any, I'm going to go ahead and write down the edges that we added. I'm doing this on purpose, not because you have to write down the edges, although I would definitely recommend it so that I can tell what you're doing easily. I'm doing this also if you're copying down this graph to give you guys time to copy down the graph too. Okay. So the weight 2 edges, we had AE. I'm regretting choosing to do this now. FG, GH. We also had the edge FJ. We also had the edge IJ, the edge KL. There should be only one more. Nope, 2 more. LP. And last one, MN. And let's count them up to make sure I didn't accidentally miss any. That looks like 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. Whew. Got them all. So there was a lot of weight 2 edges. Now, notice when we put these in here, while we ended up highlighting all of the weight 2 edges that we wanted to throw into our spanning tree, we actually, as we were going along, needed to be checking to make sure we didn't close off any circuits as we added a weight 2 edge. So in this particular case, did we actually close off any circuits with those weight 2 edges? Correct. We did not. So we're good. Actually, I was checking that as we were going along. I would have stopped us in the middle before closing off that because I really don't want to erase these ones that have a tendency to erase part of the graph too, as we found in the past. Now, next step is we're going to go ahead and look at our weight 3 edges. So as you look through that graph, you should be seeing some weight 3 edges right here. Let me pick a different color. I really don't want to use green. We'll use green. Okay. So weight 3 edges. Yes, there are several of them. So I'm just going to go top to bottom. I see CD. It looks like you guys went top to bottom too mostly. CD, we have EF. Now, watch out. This one, we are going to have to worry about closing circuits. Notice CD here did not close a circuit. EF did not close a circuit. But the next length 3 edge or weight 3 edge would be HL. Can we actually throw HL into our spanning tree? Correct. We can't. And we can't throw this one into our spanning tree because we'd actually close this circuit right here that's F to G to H to L to K to J back to F. And while you could actually remove one of the other edges in the circuit to make it not a circuit, the problem here is you want a minimal spanning tree, so it's the edge with that's the weightiest, that has the highest weight that you want to leave off the circuit. Okay. Now, Are there any other edges of weight 3 in this graph? Yep, down here at IM, can we add IM to the graph? Yep, that one there's no problem because here you're not going to close off a circuit. We just don't have enough edges yet near IM. So let me go ahead and, whoa, how did we get pink so much? All right, so we'll go ahead here, we'll add in the edges. We only added in 3 edges this time, not like the gobs and gobs of like 2 edges or weight 2 edges. So the next edge weight that we're going to look at is weight 4 edges. So while I'm writing down these edges, if you look through those graphs, see if you see any weight 4 edges. And here's the extra thing, not just which weight 4 edges, watch out for the ones that won't close off a circuit. And I see that some of you guys are already finding it. So let me be faster. I need to start being able to write and talk at the same time. Never noticed I had that problem before. All right. So it looks like from what you guys said that KO is the only one we're going to be adding in. So let me go ahead and put that in right here. And let's double check. KO does not close off a circuit, so that is definitely one that'll work. But let's double check our other weight 4 edges just to make sure. Other weight 4 edges looks like BF. Yep, that one would totally close off of the circuit. Weight 4, weight 4. EI is a weight 4 edge. That would totally close off a circuit. All right, that looks, yep, looks like KO is the only new one to add. Now, do a quick double check. Do we have a spanning tree at this point? There are 2 ways to determine that. And while you guys are determining that, I'm going to write down the edge we added. All right, I have several guesses for yes, so let us look to see about if this is a spanning tree. So in terms of in our tree, that will eventually be our spanning tree, okay? So what do we need? We need blank number of edges. So this is one way to determine that you've gotten all the edges that you need. First, what you need to worry about is you count up the number of vertices. So in this graph, how many vertices are there? I'm counting 16 as well. 4 by 4 grid if you count up your vertices, so 4 and 4, which means the number of edges we need are 15. Notice why this is a really nice thing to deal with in terms of knowing that you got to your spanning tree. As long as you haven't closed up any circuits prior, any 15 edges that you grab are going to give you a spanning tree. If you grab those edges in this order, Kruskal's algorithm tells you it's going to be a minimal spanning tree. So if we count up the number of edges that we've thrown into the graph so far, namely all these ones that have been highlighted in the variety of the 4 different colors, do we have 15 edges? I'm going to let you guys count that. What do you guys think? Do we have 15 edges there? So yeah, it looks like we've got 15 edges, which means we currently have a spanning tree. Now, there's a second way of finding our finding out whether we can stop or when to terminate this Kruskal's algorithm or if we have a spanning tree. And the second way is check out all 16 of those vertices. Okay? We already know that none of the edges form a subcircuit, so we know this thing is a tree. The only question right now is whether it's a spanning tree. So if you look at all of the vertices, in order to be a spanning tree, your tree has to include all of the vertices, which means if we look at those 16 vertices, and I realize I'm repeating that several times to try to get it to sink into your head. If you look at all 16 of those vertices, is there an edge, at least one edge, that's incident to all 16 of those vertices? In other words, if you look at the highlighting marks, do the highlighting marks actually touch each one of the 16 vertices? And the answer there is yes as well. Not going to lie, I'm definitely regretting that that original graph was in red. I do color code our examples to be a different color than the actual work, just so it's easy to see what we started with and what we ended with. But because of the color coding of this work here of getting to which step we grabbed which edge at, having the original writing here black probably would have made it show up easier. So, regrets after the fact. Okay. But that's Kruskal's algorithm. You stop once you get the n-1 edges. We got 15 edges, we stopped. Or if you're actually drawing it in the graph, once your edges actually touch all your vertices is the other way to think about it. With Kruskal's algorithm, it's probably easier to count the number of edges. With the next algorithm, which is Prim's algorithm, it's probably easier to look at your vertices. But I want to show you both ways because it works in all cases with spanning trees. Okay. Questions? Make sense? Feeling okay? That's literally it with Kruskal's algorithm. There is no more, other than having different graphs that you start with, or technically networks because you need the weights. All right, I am seeing no questions come in, so let us look at the other algorithm. Kruskal's algorithm and Prim's algorithm are almost always presented at the same time, or at least really, really close to each other. Like if you end class before you get to the second one, you wouldn't present it at the exact same time. Okay. So Prim's algorithm does the same thing. You just select the edges in a different order. Okay. So here, you're going to start off with some graph. It's a network, so it has to have weights associated to each of the edges. Typically with Prim's and Kruskal's algorithms, they're called weights as opposed to lengths, like with Dijkstra's algorithm. But in both of the two cases, whether it's Kruskal's algorithm or Prim's algorithm or Dijkstra's algorithm beforehand, the thing at the end of the day, in order to be able to use the algorithms, you have these numbers associated with each of your edges, regardless of what they represent. Okay. Now, our goal here is, again, to build a spanning tree with minimal weight. So you're looking for all of those amounts on your edges, if you add them up, to be that smallest number. So here, we actually didn't add up all of these numbers, but we could have. Actually, let's go ahead and do that real quick. So if we add up all of these numbers, and I'll actually do a little bit of scratch work here to the side, we've got, what is it? We had 1, 2, 3 edges of weight 1, so that's 3. We had, 8 edges of weight 2? 1, 2, 3, 4, yep, 8. So 8 times 2 is 16. We had 3 edges of weight 3, so that's 3 times 3, or 9. And we had 1 edge of weight 4. So if we add those all together, that's 20, that's 12. So what is that, 32? Make sure I did that arithmetic correct. Okay, so this is with weight 15. Not 15. Don't do 15. I was totally having an issue in reading or thinking edges. That weight should be 32. Okay. And I'm going to go ahead and get rid of the scratch work here. We just added up the weights of all the individual edges. Okay. Now, Prim's algorithm, and we're going to actually apply Prim's algorithm to the same exact graph in just a second. Prim's algorithm should also find a minimal spanning tree, which means a tree that has the same total weight of 32, okay? Because this is supposed to be a minimal spanning tree. So let's see what happens. So with Prim's algorithm, again, same setup, got a network. It's not a tree, because if it's already a tree, you don't do anything. We're going to build a spanning tree with minimal weight. Here's the differences. You pick some edge in the graph with the smallest weight, and you put that edge in first. Notice when we were doing Kruskal's algorithm, technically speaking, that first step would be the same, but you totally could just look at all of the weights as a whole. So we looked at our smallest weight, weight 1 first, then our next smallest weight, weight 2 first. And we looked at all of those edges collectively and then tried to add them all in. We were able to add in all of our weight 1 and weight 2 edges in our last example, but when we got to weight 3 and weight 4, we saw that we couldn't add in all the edges, and then we selected which edge we could actually add in. In our case, there was no ambiguity. It was either you could put the edge in or not. Sometimes you get options that you could put in this edge or this other edge, and you get to select. Okay. Now, Prim's algorithm is different. You pick your edge that has the smallest weight. If you have a tie, pick whichever one you want. It doesn't matter. And here's the part that's specific to Prim's algorithm. The next thing you're going to do is you're going to pick an edge in your graph with the smallest weight left of an edge you haven't used yet that is incident to any vertex already in the tree that you're building. So let me highlight the key things here. And that is the key thing here is what's going on where the other algorithm in terms of Kruskal's algorithm, at each stage, let me scroll back up, at each stage what happened, we didn't care if at each stage our tree that we were building was connected or not. In other words, as we were building up to the full spanning tree, at each stage we still had a tree because each subgraph of a tree is still a tree or a forest. But here, it was totally fine if it was disconnected. So at the stages, like for example, after the first stage of adding in all the weight 1 edges, we actually had a forest. It wasn't spanning because we started with a connected graph, but we had forest and then we merged those guys as we kept adding edges into one individual connected spanning tree. Okay? Down with Prim's algorithm, what's different about it is you're going to be building this tree essentially like fungus or mold, okay? You're going to start at one edge, the smallest one, and it creeps around the entirety of the graph, picking up one edge at a time, and each subgraph of that each subgraph of the tree that you are eventually building to is still going to be a connected tree, okay? So that's the key difference here. Now, at each stage, you're still having to go and build a tree. So at each one of these stages, when you pick up, did not mean to scroll. At each stage here, when you're picking this edge, you do have to make sure that you don't complete a circuit. So don't complete a circuit. Now, for small examples and relatively straightforward, not super complicatedly connected graphs, especially if there's no options in terms of you making a decision of which edge to pick at each stage, you have a tendency that the final minimal spanning tree between Prim's algorithm and Kruskal's algorithm does have a tendency to, if not be exactly the same, be really, really similar. It's not really a coincidence. However, if you have a lot of edges that have similar weight or a relatively complicatedly connected original graph, these guys can actually get you to vastly different spanning trees. They will still both yield a minimal spanning tree, which means the total weight associated with those two spanning trees is still going to be the same. Okay? You keep adding your extra edges, where one endpoint of that extra edge is a vertex that's already in the tree that you're building, the other endpoint's not, and you make sure that you don't close off the circuit. Okay. Notice the second endpoint not in the vertex set of the tree that you're building should guarantee that you don't have any closed circuits. And then you repeat until you have n minus 1 edges in the tree. Now, for this guy, for Prim's algorithm, same deal as before. If there's some sort of tie between edges, you get to pick which one you want to deal with. So if tie, and when I say tie, I mean with weights. So with respect to weights, your choice. Okay. And that's why, again, with Prim's algorithm, there's not a unique answer. There's not only one spanning tree that'll come out of Prim's algorithm just because you've got some choice built in if you've got multiple edges with the same weight. All right, so we're going to apply Prim's algorithm now, and I'm on purpose here, went and grabbed the exact same graph. So use Prim's algorithm. And if we go ahead and use Prim's algorithm, the very, very first thing that you say would be the edge with the smallest weight. So what edge do you guys think we should start from in this tree? Hey, you got choices. There's not one starting point. Huh, my keyboard stopped working. To answer the question back before, you guys were sending in A's and B's. The time complexity for both of these two algorithms is order n log n, where n is the number of vertices, and remember the number of edges is n minus 1. Okay. And I've got some extra resources I'll link up. They're currently in the handouts and extra information general page up near where that chart for all of our homework is listed, but I'll go ahead and link it into this area too. All right, I've got multiple choices, and the choice that we'll go with is, how about AB? It does not matter. It's totally you could pick 3 different starting points. You could pick AB, you could pick JK, or you could pick DK, and it truly does not matter which of the 3 you pick. Okay? So, step 1. So we're going to pick a weight 1 edge. We picked AB. Now, once you've picked whichever edge you've chosen, our case AB, the only edges you can now select are going to be BC, BF, or AE. And remember, you want to select the one that has the smallest what? You want to select the one with the smallest weight. Yeah, AE is the only one here that makes sense. So for this one, the next step you would do is you're looking among the edges. Oh, I don't want to write down all of these guys. We're not going to. All right, so we'll do this for a little bit. So we'll look at edges, AE. We can look at edges, BF, and edge BC. They're the only ones that are currently connected to somebody in the tree we're building. You pick the one with the smallest weight. There is no option here, so we're going to pick AE. Okay. Now, at this stage, the edges we're allowed to pick is we still can pick BF. That's not a problem. But now we have extra edges that we can select from. And remember, you're trying to find the edge with the smallest weight. The new edges that we can now select from are going to be EF and EI. I'm not sure why that 3 is in a weird position. It was, didn't mean for that to happen. So we picked up 2 new edges we could select from. Now from these 4 edges, which one has the smallest weight? And if there's a tie, you just arbitrarily pick. Yep, EF here has the smallest weight. So if we highlight that one, we're going to grab now EF. Note in terms of what we're looking at, EF is used. But because we picked up this new guy right here, we have 2 additional edges that we can start looking at. And the 2 additional edges that we can start looking at are FG and FJ. Note there's also something you can immediately do although people don't always do it, there is an edge that we can know for sure is not going to be in our spanning tree. Any guesses who that edge is? Yeah, BF. At this point, BF would close the circuit, so we know for sure that BF is not going to end up in our spanning tree. Note the symbols I'm using here. At each stage, adding extra edges, and I'm underlining the edges that we already have in the spanning tree, so you don't select them again type thing. Okay. Now, at this case, did we grab the new edges, FG? We did. All right. So now we have some edges we can look at. We can look at BC, FG, FJ, and EI. So of those guys, who have the smallest weight? Yeah, we have two options, and there are two weight edges. We have FG or FJ. So who do you guys want to throw into the spanning tree next? Hint, it doesn't matter. I saw FG come in first. So let's grab FG. That's totally the one that I'd probably pick too. Now, once we go ahead and have FG thrown in, we pick up a couple of new edges. The new edges that we pick up would be CG, GH, and GK. Notice these are the edges that are incident to that new vertex we just got, which is G. And that's how we get those three new edges. Now, we just selected FG, so let me underline that one. In terms of the edges left, BC, we could select CG, GH, GK, FJ, EI. Anybody spot somebody that has the smallest weight? Yep, I agree. It looks like a GH and FJ are the only two with weight 2. Everybody else is higher, so we get to pick. You guys sent in this one was the one that got sent in, so I'll go ahead and select that one. Okay, so FG, where's FG go? GH, excuse me, that one. Okay, so then we get new edges that are incident to vertex H, because H now is the new vertex that wasn't in our tree before. So the new edges incident to H are going to be DH and HL. Any guesses what the next edge should be? Hint, there's only one edge now that goes next. Yep, DH, you have to do that one next because that's the only edge right now that has weight 1 that is in play. So I'll underline DH. Now this does give us some new edges, and the new edge that gets thrown into play is CD, because there's only one new edge that came up from including D. Okay. So of these edges, we've got all these vertical little edges down here, all the vertical edges here, and actually both of those guys. So any edge that is above I, J, K, and L, in other words, the top half of the graph is in play. So any guesses who the next edge is that we need to add in? Yep. Oops, yep. Now, I saw you guys answered your own questions. Awesome. Thank you for that, by the way. But notice here when we went back, we actually picked up that weight 2 edge that we hadn't selected before. This sometimes happens. It turns out if you're going to get more than one spanning tree, you get the more than one spanning tree by if you have a choice between 2 edges, you pick one of them versus the other one. But only if those 2 edges would actually do something like complete a circuit. If it was what we had, which is 2 edges just with the same weight in 2 different parts of the graph, in that case, you have a tendency to just pick it up at a different stage in your algorithm. Okay, so I don't want to say that's the reason it doesn't matter which one you grab, but it turns out it doesn't. If you have a tie, pick whichever one you prefer, or the first one you saw. Okay. All right, so we just picked what? FJ. Did not mean to keep a highlighter. So we just did FJ. Now, when we did FJ, we picked up the vertex J, which means we picked up some new edges that we didn't have before. And those new edges are IJ, so everybody incident to J, JK, and JN. Now, Anybody have a guess who the next edge is that we should throw into this graph? JK? Yep, definitely. We only have 3 weight 1 edges in this graph, so hopefully we will get all 3 of them, and actually we know exactly that we do because that was our 3rd weight 1 edge. If you don't have all 3 of your lowest weighted edges in your graph, double check your work. If they combine to create a circuit, you can't have them more than 1, but in terms of this guy, we were totally able to grab them into our graph because we're very far away in the graph. All right, so let us do some scratch work. We did JK, got that one. You're right, we can totally cross off an edge. We see with this one right here, GK, we're not going to actually end up using GK because it would close off a circuit. It doesn't look like I'm able to cross off anybody else yet. And we picked up a new vertex, K right there, so we can add in some extra edges that we could use. And those extra edges would be GK that we already crossed off, so I won't write it again, KL, and the other new edge was at KO. So what do you guys think the next edge is that we should throw in? Turns out there's options. You can totally pick KL, and since that's what you guys said, let's pick KL. But you also could have picked the other weight 2 guy, which is IJ. Okay. But let's go ahead and deal with KL. With KL, I'm going to go ahead and underline it. The new edges that we can have. HL, I think it's already up there. And we also have LP. But notice, HL we can cross off because that would close off the circuit. Let me go ahead and cross off that guy. So still in play, we still have BC in play. We still have IE in play. We still have CG, where is CG? CG in play. We still have CD in play. We still have IJ in play. We still have JH in play, KO, and LP. So we're getting down here at the bottom of the graph. So you guys said IJ is the next one to deal with. Definitely. That is our weight 2 guy. So if we go ahead and throw in IJ next, where'd IJ go? IJ. We're then going to look at edges that are incident to I. So we have EI, which we already have, and IM is new. But what do we know about EI? That one we'll never use because it would close off the circuit. So EI, I'm going to go back and cross off EI. So, yep, next. All of these guys are weight 3 or bigger, weight 3 or bigger. We have a weight 2 guy in play, so we definitely should do edge LP next. Now, once we grab edge LP, we get in a new edge, and the new edge that we get in is OP, or PO maybe. So, at this point in time, the only weight 2 edge that is still in play in the graph is this guy down here, MN. We can't add him into the graph because it's not incident to any of the other edges in the graph or vertices in the graph. So that means we're looking for a weight 3 edge that is incident to one of the edges currently in the graph. Do we have that? CD? Yep, I agree. So going back up here to CD. Now, once we select CD, what does that tell you about the 2 edges BC and CG? Are we going to include them in this spanning tree? No to BC. What about CG? And that is because we'd close up the big circuit right here. CG, you also wouldn't include because that would close up the little circuit. CG go. And notice with our list here, doop, 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 all of these guys are either included or scratched off, which means we are literally only looking at what edges, these edges right down here. Now, the only ones that we can still use in the graph are currently put into the graph is OP, KO, JN, or IM. Which one should we throw in next? And I'm just going to do dot, dot, dots here because I ran out of space and I really don't want to. Yeah, we're so close. We're so close. IM. Yes, we will totally put in IM next. That is a weight 3 guy. So when we go ahead and add in that weight 3 guy, we did IM. We also now get that we can add in MN into our spanning tree. So note, the only guys that we can add into our spanning tree are MN, OP, KO, or JN. So who should we add in next? NM? Yep. Actually, that guy we've been waiting on to add in for a little while. Now, once we add in that weight 2 guy, we can now add in NO. Not going to lie, adding in NO probably isn't a huge thing that you'd want to do. Why? Because I think that's the guy with the highest weight in the entire graph. But yep, the next guy you'd add in is KO. I'm going to go ahead and underline KO. Now, I'm going to leave off the scratch work. I'm going to go back up to the graph so we can actually see the graph nicely. Notice you can do all of that stuff without writing all of those edges. No lies, I only write out all of those edges if either I'm having issues finding the spanning tree of minimal weight or articulating it. Most of the time, just go ahead and draw it in the graph. So if we look at that guy, what do you guys think? Do we have the spanning tree that's in blue and the one starting edge in yellow? Or do we need to add in another edge? Correct. At this point, we have our 15 edges. No lies, I didn't actually count them. But what we did see is, and you can see this with Prim's algorithm, that you don't see as well in Kruskal's algorithm, because of the way that this tree grew, or as we were building the progressively larger subtrees of the spanning tree we wanted, at each step it creeped its way across all of the vertices of the original graph. Once we have all of those original vertices of the original graph, in this case color-coded in blue or yellow, we are done. No is the answer. In this particular case, we did have the exact same spanning tree regardless of the algorithm that we used, and that to some extent is because the tree is just smaller. There are examples, and I looked for some of them, and I couldn't find one that forced us to have 2 different spanning trees for the 2 different algorithms. I found some examples or created some examples where we had more than one spanning tree that came out of the algorithm, and it just happened that in one of them that I chose the edge in one versus the other one. It depends on what you need. Okay, so it turns out if you just, to some extent, Kruskal's algorithm is like brute forcing it, where you're just doing, you're looking at everything in stripes. So throw in all the weight 1s, throw in all the weight 2s, throw in all the weight 3s, etc. Prim's algorithm is, if I remember correctly, Prim's algorithm was the one that was created after Kruskal's algorithm to be a little bit more fine adjustment, because depending on your situation, sometimes you need to actually be, for lack of not using mathematical terms here, creeping and growing across your graph as you build your tree. So there's pluses and minuses to both of them. They are the same order. So in terms of implementing times or times to actually go through and build the spanning tree, as long as you're not actually listing out all of the edges like what we did, it actually takes about the same amount of time to build the spanning trees from both the 2 algorithms, roughly speaking. But to some extent, it's personal preference. To some extent, it's a situation you have. Okay. For our class, I'll have situations where I'll be like, hey, use this algorithm, use the other algorithm, or your choice, you get to pick whichever algorithm you want to use, okay, of the two. Okay. But that's the idea there in terms of the two algorithms. Okay. Questions make sense, kind of feeling okay in terms of how to create the algorithms. Now, for practical considerations. Okay. Since I am not expecting you guys to write out all of these edges, although if you do it for the first time you've ever deal with either Kruskal's or Prim's algorithms, if you write out all of these edges, awesome. In terms of Kruskal's algorithm, if you want to show your work and not just the spanning tree, what we did right here of saying wait one and then just list the edges you add, that is totally fine. Okay. So that would be sufficient for showing your work if you wanted to show it. If you just wanted to give the tree, this would be just giving the tree. Okay. And it's okay if you have something that you can submit in a picture, I'm okay with just doing something like highlighting the tree, as long as I can see what you highlighted. In terms of Prim's algorithm, in order to show your work, and I mentioned the show your work here simply because one of the ways to distinguish which of the two algorithms that you used is I have to know which edge you added in when. With Prim's algorithm, like I said, I'm not expecting you to show me all of this work that we did, but if you just list which edge you added in first, second, or third. So for example, in terms of how the tree grew, how tree grew. We started off with the edge AB. We then added in the edge AE. We then added in the edge EF. We then added in the edge FG. And then it kept on going. The last edge we added in was KO. So that would be showing me that you were using Prim's algorithm by specifically showing the order in which the edges were added, because especially in these smaller examples that you would have to be given in a timed situation, you would need to be able to distinguish between the two algorithms. So something as simple as just writing the order in which you added the edges would tell me which algorithm you're using. To make sure you didn't accidentally swap the name with the actual algorithm type thing. If the direction said to use Prim's and you actually did the Kruskal's algorithm type thing. But anyway, that's not actually germane to implementing the algorithm. That's in terms of how you tell me what you did. Right, so any questions from you guys? Make sense? Feeling comfortable with these two algorithms so far? All right, I am not seeing any questions come in, so I'm going to assume that you guys are okay. So let us move on then to our next section. And I actually have a relatively large graph that sometimes, depending on time, I've covered before, running Kruskal's algorithm and Prim's algorithm over it. So I'll post that example for you guys to look over, but it's not treated any different whatsoever than what we just did. It's just a different graph, okay? But I'll post that for you guys with extra information. So let us move on to section 4.3. There's no way we're going to finish section 4.3 today, but section 4.3 deals with network flows and the augmenting flow algorithm. We're not going to probably even get to the augmenting flow algorithm. We're probably just going to get to the terminology that we're going to need to get up to the augmenting flow algorithm. So we'll be doing all of our examples and specifics of that algorithm tomorrow. There is a handout, and I linked it to both today's page and tomorrow's page on Canvas so that you can go and grab that handout. The handout is simply just a little PDF that lists out the details of the main algorithm in this section. Now, why do I mention this section? Because that algorithm is actually used in our next topic as well. So it's an algorithm that comes back and has multiple applications. So let us get our foundational definitions, our foundational thoughts in order. of the background that we're going to need to deal with what are known as flows. Now, network flows are what? You're going to start off with some network, and then we're going to deal with something called a flow. So we'll define a flow in just a second, but let us talk about what the goal is in this section. So we'll be given some network and some graph. You've got weights associated to the edges, so just like what we've been talking about in the last two sections where there's some sort of number attached to your different edges. Now, the assumption with a network flow is that it's a directed graph. You don't always see the directions, but this is typically only applicable in directed graphs. So assumption, we're in a digraph situation. Okay. Now, what's the actual goal that we have? We would like to maximize something known as a flow. Not a maximal, we want to maximize. Now, something that your author does is wow, I can't spell an M today either. He actually talks about flows from vertex A to vertex Z in your graph. That's actually a relatively common convention with respect to flows. It's sort of the key letter to indicate the start and the stop because it's the first letter of the alphabet and the last letter of the alphabet. But technically speaking, you can deal with this thing that we'll define in just a second called a flow from any vertex to any vertex. This is just, in the future, we're going to define something called an AZ flow, and it's just saying we're having a thing called a flow from vertex A to vertex Z. And again, we'll define what a flow is in just a second, such that, the flow does not or doesn't exceed any of the edges capacities. And that little apostrophe needs to actually be moved after the S. Capacities. So let's go ahead and fix that, because it's across all of the edges in the entire graph. Now, we don't know what all those terms mean yet, but we're going to define them in just a second. The easiest way to picture a network flow is similar to the example that we talked about, I think it was yesterday. It feels longer than that ago, where if you have something like pipes and you're pumping something like water or liquid through your pipes, maximizing the flow, this would be similar to saying, hey, you start at some place where you pump the liquid into the pipe system, where the pipe system represents or would be represented by the edges and vertices of your graph. So vertex A would be where you dump the liquid into the pipe system. Vertex Z would be where you're looking for all of that liquid to end up coming out of the pipe system. The flow would be the total amount of liquid you're able to pump through the system and not push any more liquid through that pipe system. And the flow doesn't exceed any of the edges capacities would be like filling up your pipes to max capacity across the pipe system and not having any of the pipes burst, though, or break, okay? So that's sort of the idea. Please note that's all in sort of a contextual or example format. We're going to get the specifics in terms of math here in just a second. In order to actually talk about our flows, though, we do need to talk about a source and a sink. So a source and a sink are defined as follows. And the easiest is by way of a picture. So your source is going to be some vertex in your graph. So a vertex. Where all of the directed edges are leaving the vertex. In other words, where it has no in degree. So if this is vertex A, the in degree would be 0. Now, there are some, not really exceptions, but snarls that can happen. In terms of if your graph is modeling where you're adding stuff at various vertices, wherever you add stuff, and I realize that's very vague, so maybe think in your head your pipe system with water. If you connect to one of the vertices and add in extra water to your system at that point, that would be where you're adding in new water. That would also be considered a source, even if it was sort of in the middle of the pipe system and you are throwing, you've got water that was already coming through that spot that was modeled by a vertex. Okay? There's ways to adjust for those issues, so that's something that you have to worry about. But in a sort of general situation, a technical definition for your source is this is where stuff is coming into the system, so you're looking at vertices that have no in degree. Okay? In other words, this is where you started from. Now, a sink is exactly the opposite. So this is a vertex, we'll label this Z, where everybody is coming in to your vertex, and it's called a sink. Think like an actual kitchen sink, the water going down the sink. What happens is if everything's working correctly, it should not be coming back out of the kitchen drain. Okay, so here, this is a vertex where stuff comes in but doesn't leave. So vertex in the graph where the out degree is 0. And I used an A and a Z because when we start looking at A and Z in the future, A is going to have to be a source, and Z, as we use it in the future, is going to have to be a sink. Okay. Now, in an arbitrary network, can you have multiple sinks and multiple sources? Yes, and that's something we'll have to adjust for before we apply the algorithm that we're going to care about in this section, which is our augmenting flow algorithm. Okay. So now we are almost ready to deal with the next thing, which deals with an AZ flow. So I've got the prep up for it, and then we're going to do the details. But before we do that, I have totally thrown a question to you guys. So let me go ahead and share this. I know it's going to get really tiny. Let's you guys see if you can't spot your sources and your sinks in a graph. Okay, so this is up on your Poll Everywhere site. It's the same URL we've had for the entire class. So see if you can't spot the source if one exists in network. Note, you don't have to have a source, you don't have to have a sink. You can have multiple, you can have exactly one. Okay. I'll give you guys a little bit of time to make a guess there. All right, it looks like most of you guys have a guess. The last couple of you guys want to make a guess? As we're about to have a question 2 that we're going to switch to. So as soon as we switch to it, you won't be able to make a guess for this one. All right, it looks like everybody's made a guess, so I'm going to switch us to the next question. Just a second, let me activate it. And go figure, this one is the exact same graph, and now it asks to see if you can't identify the sink. So let's just see if you can spot that one. If it exists. Again, there could be multiple sinks, there could be one sink, there could be no sinks. It all depends on how those directed edges are actually put together in your graph. don't overthink these. These descriptions of sources and sinks are totally descriptive. They weren't named after anybody. They were literally, I mean, probably one of the ways to remember them is very much dealing with like water and pipes, source, sink. Where do these get a descriptive picture in your head type thing? All right, it looks like most of you have made a guess, but there's still about 10 of you left who haven't made a guess. So I'll give you a little bit of time to make a guess, and then we'll look to see what you guys thought. Okay. But you want to go ahead and put in a guess because I'm about to move that page, and when I move that page, you won't be able to enter in a guess. All right, it looks like most of you have entered in a guess, and to make sure that we can actually talk about an AZ flow, I'm going to have to cut you guys off right there. So I'm going to stop sharing the work that we're working on, and so only share the one screen with you, and we are going to go backwards. All right, so for this one, in terms of a source, it looked like the vast majority of you guys totally get the source. It's right there, and what happens, that is totally right. Key thing to look for is this is the only vertex where everybody's leaving. Every other vertex has some edge going in and then some edge going out, or it might be a sink. Okay? So good job, you guys got it. Now, in terms of the next one that we've got, again, it looks like the vast majority of people had a guess of E. That is correct. E is totally a sink right here. One of the ways that I started remembering a sink when I first did it, because when I heard the word sink and source the first time, I was like, these seem like just bizarre words. What are they referencing? Is totally thinking here, the source is where stuff is getting pumped into the system. The sink is where stuff is like, the first picture I made in my head was something like quicksand. You literally step on it, it sucks down, and you never leave. Okay? So that would be one of the ways to think about with these two guys. Now, let me go back and share the other thing with us. And that actually is where it came from. So the comment was, it makes me think of a kitchen sink. That apparently is actually one of the things that people thought of when they created the name. That wasn't what I thought of the first time I saw it, but that's the common thing that everybody says. If you see this in other classes and the teacher gives you an analogy, or whoever's talking gives you an analogy, they're probably going to reference something like a kitchen sink, because that is totally what people, the main analogy that people reference when they're dealing with sinks. Now, that being said, let us now talk about a flow, because a flow is going to be going from your source to your sink, or really the vertices that are sources and sinks have to be treated a little bit special, if you will. So I outlined this while you guys were answering. So your AZ flow, or you replace the letter A and Z with whatever letters you have for your vertice names, where the A is where you start, or it's your source. Wow, apparently I can't spell today. And your Z is where you end, or this is your sink. Okay? So this is a directed network, so you have weights associated with each of your edges. In these type of networks, the weights are considered capacities. Why? Because the flow is going to be pushed along the edges, and the maximum flow that you can have on an edge is going to be the same as its capacity. So this water analogy, there's totally a reason why I've been saying it multiple times. Okay? So you've got some integer valued function. This means the outputs here are only integers. This f of e is the flow. And specifically, it is the flow on each edge. So E here is an edge. Okay. Now, here's how this flow, this function, that is a function on the entire network, but you plug in the actual objects you plug in from your entire network would be the individual edges. On each edge, the flow is maybe 0, but no more than whatever the actual capacity is. So your book says K, so I'll do K of E. Okay? So flow is somewhere between 0 and capacity. No negative flows. It's not a thing. I mean, you could use it to represent that your directed arrow went in the wrong direction, and some people do that. But we're not going to deal with that right now. In terms of if you pick any vertex in your network that is not a source or a sink, you have to have the following property. The total flow that goes into that vertex has to equal the total flow that flows out of the vertex. To put it in actual mathematical symbols, this would be the sum of the flows, where E are the edges that are coming in to your vertex V, and that has to equal the sum of the flow of the edges that are going out of your vertex. Okay? So that would be the idea here in terms of the mathematical symbols. Personally, I find it easiest to remember it in terms of the words. I think that's not normal. Normally, I remember it more in terms of the symbols, but total flow in has to match total flow out at each vertex. It was I did a capital IN here, so in, not an LN like a log. It's just, and same here, capitalize the word out as well. If you want to do lowercase, that's fine. It's often with an uppercase, and we're going to see this larger down here in just a second. Now, if your vertex actually is a source or a sink, so notice here, this here is again in, so these are all of the edges that are coming into your source. So if this guy is your source, your edges coming in. Please note, we're assuming as a source that that doesn't normally happen. What has to happen? Well, those have to be those guys coming in have to actually have a flow coming in of 0. In terms of your sink, what happens with a sink? This is where all your edges are coming in. If you actually did have an edge leaving what you thought was your sink, well, in terms of the flow on those edges has to be 0. Okay? And specifically here, you're looking at your directed edges coming in to the source, and these are the directed edges coming out of the sink. So when we apply it to the random vertex, same deal, edges going into the vertex, edges going out of the vertex. Okay. Now, in the last couple of minutes for today, let us look at an example of somebody and check to see if it looks like it is a flow or not. And then next time, we're going to specifically look at our augmenting flow algorithm. So suppose we have the following example, and you guys check and see if you think that this is a flow. So I'm going to do a relatively straightforward network. So here's our graph. The question that we want is this a flow? So first thing I'm going to do is I'm just going to put the network down. So we've got A, got B, got D, Z. Normally we wouldn't label a Z. Did that just because it's going to turn into a sink. And so I can use the same words, AZ flow. C, there's E. That was trying to be an E. Then we have an E to D. B to E, and one more edge, C up to B. Now, there are two things that we need to worry about on this. In terms of the network itself, we need to know the capacities of each one of these edges. So if we look at the capacities of each one of these edges, what are we going to do? We have individual numbers right here, which will be going to be 3, 5, 4, 3. Oh, I missed an edge that I want. D to C going backwards, 3, 2, vertical guy, 2, 2, and 4. So those guys are all the current network. Notice we know it's a network graph with weights on it. Now, in order to do the flow also has values associated to each edge. So that means there's actually two values associated with each edge. So see if you believe if this guy is a flow or not. So when looking at this, here's the rubric. The numbers, if you have 4, 2, the 4, here's the capacity. The guy inside is the flow number. So this is the F of E. This is the K of E. So that's how to read those numbers. Okay. So in order to check to see if it is a flow, there are, well, two things you check. One is specific to not the source and not the sink, and the other one is specific to the source and sink. So our source here is A. Our sink here is Z. The first initial thing is everything coming out or leaving the source and everything coming into the sink, it's got to be the same amount or it's not going to be a flow. So if we look here at a source, notice the amount leaving, total amount leaving the source is what? It's 5. Coming into the sink, notice what happens. The amount coming into the sink on the flow, these are the black numbers. That sum is also 5. So at first glance, it's a possibility that's a flow. Then you have to check all the other vertices, and you look at the sum of total in and total out. So if we look at vertex B, notice the total flow in is what? 3 plus 0. 3 plus 0. Now, the total flow out is 2 plus 1. And in both cases, it equals 3. If that's true on all of the vertices, you're potentially going to be a flow. Notice automatically all of these numbers in black have to be smaller than your capacities. Nobody's negative. So as long as there's 0 and or between those red numbers right there, base case good, total out of source equal to total in sink, and the total in and out at each vertex is the same. And if you notice, as I was writing the numbers across, and I didn't say them as we were going across, I was actually in my head splitting the flow across the network. This one, as long as I didn't make a mistake, should actually be a flow. But how to check to see if it's a flow is exactly what we just did here at vertex B, is you check to see if the total inflow and the total outflow is the same. And the other thing you check is the total outflow from the source equals the total inflow from the sink. And the third thing you check is you make sure that all the flow numbers are between 0 and whatever the capacity is or the weight is on each edge. Okay? So this one should be an example of a flow. Okay? But that's it for today. Next time, we will look at the augmenting flow algorithm. The augmenting flow algorithm says you start off with some flow and then you augment it, i.e. you make minute adjustments to get it to be a maximal flow. In other words, you push the most amount through your entire network. But we'll do that next time. Well, with the augmenting flow algorithm, You can think of starting it in one of two ways. You can either start it with the flow is 0, meaning there's no flow on, and so the first pass through the augmenting flow algorithm is actually creating that first flow. Or you can actually just create your own sort of, I think it's close to the maximum flow possible, and then you use the augmenting flow algorithm just to switch it up. In terms of this specific example, I actually made up the numbers as I went along. So in terms of something that you would see, you would have been given all of these black numbers, and your question would have been, is this a flow? I on purpose did those black numbers in black, which is normally just our scratch work, because I wanted them to stand out from the red numbers. That is one way to think about it. So the question here was, is a source a vertex with no inputs in a sink the opposite? Yeah, that would be a way to think about it. Now, it's not the only thing, and we're going to see how you adjust for weird, stupid sources and sinks that you need to adjust for, but that's a good way of thinking about it, yes, for your source and your sinks. In terms of capacities, your capacities always have to be given to you. Yes, and that's actually the issue. A graph can have multiple sources and multiple sinks, and we'll actually start off with that example next time. We'll have a graph that has multiple sources and multiple sinks and has a source that's not a true source, so it actually has some stuff coming into it, and so we'll have to adjust to actually make it only one source and only one sink, and nothing coming into the source and nothing leaving the sink. You need that strict definition. And in math, the word strict is just meaning really, really precise, no exceptions. You need that strict definition of source and sink for your augmenting flow algorithm and some of your other algorithms, because they can't handle if you have sort of weird cases of, not technical term here, stupid sources and sinks. So I'll show you guys what that adjustment is to fix any issues. And that'll be the first example we start with next time. So next time we'll start with that first example, then we'll look at a couple of the definitions we didn't get to, and then we're going to jump into our main algorithm. Okay, yeah. Oh, I see a private comment, just a second. All right, so at this point, I'm going to go ahead and stop our recording, which I probably should have stopped a little bit ago. If you guys still have extra questions, I'll hang out for a little bit, and I see there